Assalamu alaikum everyone, welcome to the course of real-time embedded system. Today we will continue our chapter number 5, program design and analysis. Previously we have talked about program optimization and we have seen program level performance. Today we will talk about loop optimization. In this lecture I will discuss loop optimization techniques. Let's get started with today's topic. So basically loops are important targets for optimization because programs with loops tend to spend a lot of time executing these loops. There are three important techniques for optimizing loops. Number one is code motion, number two is induction variable elimination, and number three is strength reduction. So let's get started with one of them. First of all, we'll start discussing code motion with the help of examples. So code motion basically lets us move unnecessary code out of the loop. If a computation result does not depend on operation performed in the loop body, then we can safely remove it out of the loop. Code motion opportunities can arise because programmer may find some computation clearer and more concise when put in the loop body, even though they are not strictly dependent on the loop iteration. A simple example of code motion is also common. Consider the following loop. You can see this loop for I is equal to 0, I is less than n into m, and I plus plus. And then we are putting the value of a of I plus b of I in z of I. So the code motion opportunity becomes more obvious when we draw the loop CDFT. So we have drawn this CDFT, control data flow graph. This is initialization, this is decision, then this is assignment. So as long as I is less than n into m, we are doing this and then we're updating the loop variable. So the loop bound computation is performed on every iteration during the loop test. Even though the result never changes, we can avoid n into m minus 1 unnecessary computations. So this is unnecessary computation n into m. By moving before the loop. So why we are doing this inside the loop? We can simply compute the value of n into m because it's not changing within the loop. So this is code motion. We can move this piece out of the decision. So rather than having this I is less than n into m, we can have a single value or fixed value that is the result of n cross m. Okay. So as you can see here, we are moving this out of the loop body. So this is the final code motion. We have initialized I is equal to 0 and in x we are putting the result of n cross m and then the condition is on x. As long as I is less than x, we are getting into the body of the loop and then we are incrementing our loop variable. Let's move on to next slide. So the next technique for loop optimization is induction variable elimination. Basically our loop index is our induction variable. Induction variable is a variable whose value is derived from the loop iteration variable's value. The compiler often introduces induction variable to help it implement the loop. Properly transformed, we may be able to eliminate some variable and apply strength reduction to others. A nested loop is a good example for the use of induction variable. As you can see here, we have a loop that is nested loop and we are just assigning the values of B matrix to Z matrix. Now rather than using rows and column, we can simply use I into m plus j. For each array in iteration, as I've told you that we can transform a two-dimensional array into one-dimensional array using this I into m plus j. So rather than recomputing I into m plus j for each array in each iteration, share induction variable between arrays. So we can share the induction variable between array, increment at the end of the loop. So we are going to look at this. So the compiler uses induction variable to help it address the arrays. So we use induction variable to help it address the arrays, because we know, if we know the start of this z vector and we know the start of this b vector, so what we can do, we can use induction variable to help it address the arrays. So it is just kind of an offset. So let's take an example. So here we have in this code, in the above code, zptr, this zptr and bptr are the pointers to the head of z and b arrays. So these are the pointers to the head of z and b array. Whereas zb induct is the shared induction variable. However, we do not need to compute zb induct in each loop iteration. Since we are stepping through the array sequentially, we can simply add update value induction variable. So what we can do, we just need to increment the value of z induct. So this is kind of a strength reduction. Okay, so this is kind of a strength reduction. So we have seen two things: induction variable elimination. So we are eliminating and then we are doing strength reduction. So this is our induction variable which we have assigned out of the loop. Then we have first loop, nested loop, same thing, pointer pointing towards the head of the z array, pointer pointing towards the head of b vector, b array, and then we are adding the induction variable, and then after each loop we are incrementing the induction variable. This is a form of strength reduction since we have eliminated multiple multiplication. So we have this multiplication. I have told you what is strength reduction. Rather than doing multiplication, we prefer addition. So we have eliminated the multiplication from induction variable computation. Strength reduction helps us reduce the cost of loop iteration. Consider the following assignment. For example, if we have y is equal to x into 2. In integer arithmetic, we can use a left shift rather than a multiplication by 2. If the shift is faster than the multiply, we probably want to perform substitution. This optimization can often be used with induction variable because loops are often indexed with simple expression. Strength reduction can often be performed with simple substitution rules since there are relatively fewer iterations between possible situations. So what we can do, we can eliminate multiplication. For example, if we have to perform y is equal to x into 2, so rather than using integer arithmetic, we can use left shift. So in this slide we will talk about cache optimization or cache analysis. A loop nest is a set of loops, one inside the other. As we will show it to you in the next slide, loop nests occur when we process array. A large body of techniques may be developed for optimizing loop nest. Rewriting a loop nest changes the order in which array elements are accessed. This can expose new parallelism opportunities that can be exploited by later stages of the compiler, and it can also improve cache performance. So we will concentrate on the analysis of loop nest for cache performance. Now let's move on to next slide. So this slide basically represents array conflict in cache. As I've told you that cache conflict can occur when two arrays try to access the same cache block. So these are two arrays in cache main memory, and one is at 1024 and starting is 00, and another is at 409 and starting with B00, and the size are mentioned in your book that we have 265 rows and we have 4 columns, and the line is 256, the cache line is 256, 4-way set associative cache with 4 words per line. So if we see that both of these are trying to access the same cache block, so conflict can occur. How to fix this conflict, or how we can eliminate the cache conflict, is by moving this array down to 4100. So if we move this array 4099 to 4100, we can fix the conflict. However, that fix won't work in more complex situation. Moving one array may only introduce cache conflict with another array. In such cases, we can use another technique called pairing. So if we extend each of the rows to have 4 elements rather than 3 elements, with pairing word placed at the beginning of the row, we eliminate cache conflict. So in this case, B00 is located at 4100 by pairing. Although pairing wastes memory, it substantially improved memory performance. In complex situations with multiple arrays and sophisticated access patterns, we have to use a combination of techniques. And these techniques are relocating arrays and pairing them to be able to minimize cache conflicts. So one of the easiest way to eliminate cache conflicts is to pat words, okay, so which is usually known as word pairing. So as I've told you, array element conflict because they are in the same line even if not mapped to same location. So as we have seen that the array location was different, but they are in the same line even if not mapped to same location. Solution: move one array. Okay, so we can move one array to some other location, or we can do pairing arrays. As I've told you, pairing arrays will solve this issue. However, moving array will make conflicts with other arrays. So performance optimization hints include: use page mode memory access. Make use of page mode access in the memory system whenever possible. Page mode reads and write eliminate one step in the memory access. You can increase use of page mode by rearranging your variables so that more can be referenced continuously. Analyze cache behavior to find major cache conflict. Restructure the code to eliminate as many of these you can. Instruction conflict can be handled by rewriting code, rescheduling. Conflicting scalar data can easily be moved. Conflicting array data can be moved or paired, as I have shown you in previous slide. Lastly, we can improve the performance by using register efficiently. Group accesses to a value together so that the value can be brought into register and kept there.